All right, welcome to Unit 4 on conservation of energy. In this first video, we're going to be talking about the first lesson. Lesson number 1 is on work. So, before we jumping into this example number 1 problem that I have written up here, I'm just going to give a little bit of a rundown on, well, what work is. So, to keep it simple, to keep it short, all work is a representation of energy that we can either give to or take away from an object based on a force that we apply to it. So we can push or pull an object down the road. If it's speeding up or if it's slowing down, we're doing some value of work to it. Okay, so the formula that is given is work is equal to a force times a distance that it's applied over, times, and then it gives us this cosine theta value. Well, this is a little bit of a bonus value to make the solving simple. We can really solve for force without that cos theta value, but it often does come into play. So we'll keep it up here for our first example. So if we were to apply a force on an object, and that object were to move or to be moving, we could say that the force, the magnitude of the force that we apply to this object, times the distance that that object travels, is going to be the amount of work done on it. Now, what's important here, there's two important side notes on this. The first of which is that the force that you are applying has to move the object. If you can push as hard as you want, you could be sweating up a storm, pushing on an object, but if that object does not move, you will not have done any work to it. You have added no energy to it or taken any energy away from it. All right. The second important side note on this is that the only force that you can consider being applied to an object is the value of that force that is in the same direction as the movement. Now, you might say, well, what's that mean? Well, if this block is moving 6.2 meters per second to the right, and we are applying this force at an angle, only the x component of this force counts towards the work done to it. Right? Our motion is in the x direction, so we can only consider x direction forces. So this 710 newtons is all great, but if we were to take the adjacent side of this to solve, it would be a cosine function. And that cosine function up here is what takes that into account. So really all this cos value is doing is saving you a little bit of trigonometry and just plugging it right into the value. Something like this, F2, where the force is in the same direction as the motion, you could just say that this is cos of 0, like the angle that you're pushing at is 0 degrees different than the angle of motion. Cos 0 equals 1, and so you would be multiplying your answer here by 1. So if you're pushing in the same direction or pulling in the same direction as the motion of the object, you can just ignore this cos theta value and just do force times distance. All right, with that said, let's jump into this first example. I'm going to start solving it just below here. I think I have enough space to do both parts A and B. All right, so I'm going to write this equation out again. Work is equal to force times distance times the cosine value of theta. All right. Now, they started us off with an angled problem. They didn't start us off with something super easy, but that's okay. Really, it's not too complicated, and I'll try to walk you through each of the steps. So, it's asking for force 1, which is 710 newtons at an angle. So yes, we know the magnitude of force 1, so we can check off that we know force 1. The distance that this thing travels, however, we aren't directly given it, but we are given the information that this object is moving at 6.2 meters per second at a constant velocity for 8.9 seconds. So constant velocity and time, we can just say that, not force, we can say that distance is equal to velocity times time, So distance is equal to, what's this, 6.20 meters per second times 8.90 seconds. So the distance value here works out to be 55.18 meters. All right, so now we have the distance that this travels. The last thing that we're going for here is this cosine theta value. Well, if we're looking for the force that is pushing this thing to the left, we're looking for this one, right? That's what we want. So that is the cosine value of 710. So what's saving us a little bit of work here is we can just fill this value in with cosine of 25 degrees. And that's what I'm about to do. Work is equal to 710 newtons. And I do have one more thing to add to this, but I'll finish this step. Times the distance that it travels, 55.18 meters, times cos of 25 degrees. All right, so the thing that I wanted to mention, and I should have maybe started the video with this a little bit clearer, but this force is pulling in the opposite direction to the motion. Right? This force is pulling at 25 degrees away from the exact opposite of the motion. So what can we do here? There's two things that we can do to fix this. First thing is we are looking for the direction that goes in the opposite direction. This value here, we know that this is going to be opposite motion. So when we get our value for work, we could just put a negative value on front of it, because we could say that this direction is positive, this direction is negative. Okay. Or I'm going to be showing you something in future problems that we could start applying now. Now this is going to take a little bit of explaining, but I know that all of you will be capable of it. So if we have a Cartesian plane here, all right, and our motion I'm going to do here first. This is our motion moving to the right. Really what this cosine value is the difference in angle between our motion and our force. Okay, so now if I have our force pulling up this way, that's something which is, this is 25 degrees. Well, the difference in these two is this angle. That angle is the cosine angle here. And so if I were to calculate that, this would be 180 degrees minus 25 degrees. So it'd be 180, 170, 160, 155 degrees difference between our applied force and our motion. So rather than using this cos 25 degrees, because this is opposing motion, I'm going to switch this up. And I'm now going to say cosine of 155 degrees. That is going to give us a negative number. In fact, the number that gives, well, I had it worked out, but my calculator went to sleep. Cos 155 is negative 0.487. So that in itself will make this a negative work function. So let's plug this into our calculator then. Work now is going to equal negative 35,507 joules. And if we want to put that into scientific notation with 3 sigdigs, we can say that work done by force 1, so say work 1 is equal to negative 3.55 times 10 to the 4 joules. All right, so part 1 is complete. Let us move on to part B. So part B, I'm going to make myself a little divider line just to keep things tidy. And part B, start this one in blue maybe. Okay, so we're told that this object is pulling in uniform motion. Actually, part B is going to be quite straightforward, I hope. So constant velocity means uniform motion. We just finished a dynamics unit. From dynamics, we should know that if it's moving at a constant velocity, F net in the x direction is equal to 0. Which means that this force 2 pulling to the right is pulling just as hard as this F1x component is. F1x is equal to F2. Okay, so let's write that out. Can say that F net is equal to the sum of all the forces. So on this we have F1x plus F2. All right, and then we can put some values in here. 0 is equal to... Well, actually, you know what? I'm going to just change this up just a tiny bit, just to simplify, I think, for you as well. We're going to say that F1x we know is negative because it's pulling to the left. So let's just start off by saying that this is negative F1x plus F2. Is that how I want to do it? 1 second. Let me just process this. F net is equal to F2 minus F1x. 0 is equal to... Oh, I do want to keep this just positive values for now. Okay. Because we've always done it this way. This is the sum of the forces, and this is going to have a negative value. We know that this is going to have a negative value because it's pulling to the left. So let's keep it like this, and then say, filling in numbers now, 0 is equal to F1x plus F2. And if we want to solve for F2, F2 would equal negative F1x. What this statement says here, it says that force 2 is going to be equal in magnitude to F1x, but opposite in direction, which I think we can see from the diagram. If this is going to be pulling to the left, and this is pulling to the right, but it's maintaining a constant speed, equal magnitude, opposite direction. Okay, well, if work, let me change my color up to do work. If work is equal to force times distance times cos theta, okay, and work is equal to, if force 2 is equal to the same force as F1x, really it's going to be this 710 times this cos 155, right? The magnitude of that value is going to be the same. The distance is going to be the same. So realistically, what we can say is that since the force is equal, since the distance is equal, the work done is going to be also equal, but in the opposite direction. So for this question, we can just put that this is 3.55 times 10 to the 4 joules. But it's positive because it's moving this block or trying to add energy to this block to the right. All right, that is this first example problem.